Let's start out with Jesse. Jesse, can you tell people who you are? I think you've been here before, so they will recognize you.
Yeah, I'm the same Jesse that was the Jesse here before. And I've been researching the shape of the contour of the surface of Earth for a few years now, and it's been very interesting.
Awesome. And we've got Flatzoid here for the first time. Flatzoid, welcome to the show. Nice to have you.
Hola. It's good to be here, guys. Thank you, Jaron, for hosting this for us. I think it's going to be an exciting evening. Looking forward to the debate. Did want me an art for the specific topic, so I think it's going to be great. So yeah.
All right, we'll let Flatzoid choose because he's never been here before. You can choose modern day debate or Debatism X for the coin toss. Which one do you choose?
Debatism X.
Okay, let's see how that goes. He's choosing the right one. Let's see. And there's your flip. And it is, don't be modern day debate. It is. Modern day debate. Yeah, see, that's what happens. All right, Jesse, you get to choose. You want to go first?
I don't care. Do you care, Flatzoid?
No, you go ahead. It's fine.
All right, I guess I'll go first.
Okay, so you got a minute intro just to, I guess, present your opinion, your case, and then we'll do Flatzoid in a minute, and then we'll get started with 30 minutes each, and you guys know the rules from there. So go ahead. Your minute starts whenever you begin, Jesse.
All right, could I share my screen for that?
You can.
Let's see if I can remember how to do this. Share screen, the green share screen button. And select a window.
Why isn't mine working either?
And it's called Measurements 110, and it shows up. And
don't see it yet. Okay, now we see it. Let me get that on there. Okay, you are good to go for now. I'll get you guys' pictures on there in a second. But we can see the screen.
Oh, okay. So you can see my... Oh, cool. All right. So basically, this is the technique of much of my exploration of the contour of the Earth's surface is measuring angles and using angles and distances to get the height, or the delta height, the difference in height between the observer and the target. And so you can see here I have a tree. This is just an example. I'm measuring an elevation angle of 31 degrees. I know the distance, and so I can calculate the height of that tree using the rise over the run and the arctangent, or the tangent of the angle times the distance, or the run, and to get the height. And we can obviously go over this in detail. I measure using a device which is much more sophisticated than this diagram, but it is basically the same thing, a level and a protractor. And I measure to the tops of things at different distances and develop a drop over distance curve. So how's that?
Okay, excellent. And we've got Flatzoid up next. Go ahead, Flatzoid. Your time will start when you start talking.
I would also like to share screen.
Okay.
For mine.
Let me stop.
But he's going to have to end his first.
I got it. There you go.
Sure. Thanks. It's going to get the right Lemon presentation. Sorry, I'm just going to get a slideshow. Okay. Is it showing?
I don't see it yet.
Share.
There it goes. Now it's coming.
Okay.
There you go. You're on.
Okay. Perspective versus the physical curve. Is it optical or physical? Well, this is what he first presented to me, and I just wanted to see what I could ascertain from what was shown, because it's very specific of what he wanted to show. So what I saw is the level was made at the feet. So that's just a question I'll ask, because he's showing level at the feet of the observer and not the theodolite, which is just something I picked up, which is weird. The angular size of the mountain, is it? It's in contention because he's making a deduction on it has to be this size on a flat Earth by taking orthographic view, which doesn't represent perspective completely, because perspective is based in 3 dimensions and orthographic is only 2-dimensional. And then I said, is it expected on 2 different models? So could it be a straw man? And is this a calculation or a measurement? Then it's based on his second thing that he just brought up, which I said orthographic view is only 2-dimensional. So it ignores the dimension other variables that need to successfully to call it perspective. If the peak was always above no matter the distance, even knowing we have convergence to perspective. That time.
Okay. Thank you very much. All right, so we're going to set the clocks at 30. You guys each have 2 buzzers. We checked them before this for the debate. They work, and so we will get going here. And so, yeah, you can buzz in whenever you want. Otherwise, it's going to be Jesse starting us off, and Jesse, you can go 30 minutes if you want.
All right. Actually, since Flatzoid, you want me to call you Flatzoid, or do you have a name you prefer?
Doesn't matter. My name's Keith, but you can call me Keith.
Oh, that's a lovely name. It's quicker than Flatzoid. Okay, so since Keith saw my material, since I sent it to him earlier, and I think you might have some questions. So, would you like to question me on my material, on those 2 diagrams that you showed that I gave you?
Okay, yeah. Sorry, is it my time now?
That's fine.
Okay. So, what I actually wanted to do was with my presentation, I was trying to, if I had the time, to get to showing why it would only be optical and not physical. Would that be fine if I do it that way rather than ask? Because I understand what your diagrams are saying. I would just like to show why it's rather optical than physical. Is that okay?
Okay, can I just respond then briefly to a couple questions you raised? One was, you said, how come it's showing the angle from the feet? That's a good question, but obviously if the mountain was 8,934 feet tall and the guy is only 6 feet tall, if I drew the guy to scale and drew the angle from the guy's eyes, the guy would just be one black dot. So, and since I drew these mountains scaled, actually I took a ruler, they're actually drawn to the same scale. The top of that mountain where the guy was standing was the actual scaled height, not his eyes. So that's why.
Okay,
and then the rest is just the measured angle, and that's what it was. And then the expected angle, which is using standard trigonometry. So.
Great. Okay, yeah. Because no, the reason I was just nitpicking there. That's not saying
Yeah.
The question mark. It wasn't really that serious. Okay, I'm gonna share my screen again then quickly, so we can. Okay, you guys can see on the screen.
Yes.
This was actually from your video, one you did. So the first argument I'm going to be doing is refraction causes things to appear in another position that they actually aren't, and what you showed here was when you put a Fresnel lens in the way, the coincident angle caused the mountain to be visible. So you were obviously trying to show refraction can cause things to appear over a curve, to say. But this is also an anomaly that can cause things to appear downwards. Notice that you were below here, and if you were on like a mountain or something as well, you would be also looking upwards or downwards, doesn't really matter. But the point here is the lensing effect can cause something to either go up or down based on your incident angle as well. Then next, I had the same example with Rob Skiba. He also did the same thing. This was on a table. He used a Fresnel lens, which caused the buildings, just by placing the Fresnel lens and moving away from it, to have this bottom-up obstruction, which made it seem lower and more compressed because of the way light refracts. And then the next one I would have, Skyfree, showing refraction causes things also to either vanish bottom up or totally be obscured straight from just having refraction. Really awesome stuff. The next one that Skyfree did was really awesome. This was with a laser. They were that on the left where it says no refraction, that is the laser pointing towards the wall with the camera showing on that little screen in the bottom. When they added the refraction by opening the door, it looks like it's curving and that you don't see the laser anymore, but the laser itself is still hitting on exactly the same point on the other side. So it shows the location of the light doesn't change. Only the observer watching the point of contention is what's having an optical change. The next thing I wanted to bring up as well was foreshortening can cause things to seem to be blocked. So waves or another mountain or even fog, anything, rain, clouds, that can cause things to also be blocked, and because of perspective, it has a convergence downwards and upwards. And then last but not least as well, we have foreshortening. and diffraction. This was done by Life is Short, and that little white light was above the water, and when he dropped it, it showed half bottom up, and when he dropped it even more, it was no light at all. This had a whole bunch of variables that are done on a flat lake that is wouldn't even have curve, even if you wanted to have it on your model. The last one is just parallax. You'll probably understand parallax. If you line of position to reference would either cause the one to be lower or higher, or just based on how high or low you are. So it has nothing to do with Earth curve. And then this was based by Mad Melon, where people love to say, this was exactly the same location, same height. See, his camera was higher than the water level, so the Earth appeared higher. So as soon as he put his camera lower than the water level, he made the water level rise and the back foreground drop. This is all just due to parallax. That's all I needed to show for now.
Okay, and you go ahead, Jesse. Oops.
All right, I had to unmute. Okay, so I love Skyfree stuff. Skyfree does some really nice stuff. The lake, or the little pond, was warmer than the air, and also his floor was warmer than the air, and the Fresnel lens that caused bottom up obstruction was also top heavy, so it had the more dense part at the top and the less dense part at the bottom. So what all of those, yep. See, I've got a prism right here, and the ones that Scaba was doing had the thicker part at the top of each little ridge and the thinner part at the bottom. So yes, that all of those examples would have and should have caused bottom-up obstruction because they were causing light to curve upward. They were bending it upward. They were redirecting it upward, and that causes things to appear lower. What that doesn't explain, though, is why we have bottom-up obstruction and the top being dropped down in cases where there is not a top heavy density gradient, where it is more dense down lower and less dense up higher, right?
You passing? Or are you still talking?
Yeah, no, if you ever, yeah.
Sure. There you go.
Okay, sorry, my buzzer didn't want to work. I actually tried a few times. Okay. First of all, a Fresnel lens doesn't have denser and less dense parts. It's a Fresnel lens. It's literally based on horizontal and perpendicular lines. So it's based on how the light by an incident angle hits it. So there's no denser or less dense parts unless you have a curved Fresnel lens. I do love that you're making my point, though, that a lens would cause the deflection of the apparent position, which makes my point, then it's optical and not physical. Also note that I can show demonstrations also where you see, okay, showing it on screen. But anyway, like I'm saying, so like convolution Fresnel lenses. But what I'm saying is now you're making my point that it's optical. Okay. It's not based on the density. If you saw that, like your thing there, the curve, it's still the same thickness as all those ribs in there. So the densities are still the same. It's just got to do with coincidence angle. But yeah, it's optical, not physical. And I said I can also show demonstrations where you can add heat, and it would also give differences in refraction index. So I pass.
Okay, go ahead.
All right. So and I would love to discuss refraction too. Refraction, though, is separate from perspective, because refraction actually causes light to deviate from a straight path, right? And perspective is called linear perspective because it's based on the idea of straight lines, right? No?
You can both talk, that's fine.
Yeah.
Oh, okay. Now, actually, linear perspective is art. It's detailed to try draw based on a convergence to what you see in reality. It doesn't mean the light is not bending. Light doesn't bend, I agree, it goes in straight lines. The refraction causes the light to appear to bend. Okay, so again, making my point that it's only optical. And refraction is all part of perspective because perspective is three-dimensional. When you're looking out in the distance, just like your observation for the mountaintop, you would agree that the further away something is, the less accurate your device would be, your theodolite.
Oh, I agree, but I think that's irrelevant. But let me share my screen.
Go ahead.
It's called laser light. Now I gotta find it in the list.
Okay, you're on.
So gradient refraction actually does cause light to curve, physically actually curve. And how I know this is I created a density gradient with salt in the bottom of a fish tank, and I took a aluminum beam, which is this lower green line, and I curved it. I physically curved it, and I put 3 eyelets, 3 copper loop eyelets on it, and then I placed it down in there, and then I shone the laser beam through, and it went right through the center of all 3 eyelets. And since the eyelets followed a physically curving path, and the laser beam was going through the centers of all 3 of them, I concluded that the laser beam itself was actually following a curved path. Does that make sense?
Yeah. Would you be able? Do you have another picture of showing from the other angle, the side, the front view or the side view of the fish tank where the laser's pointing in?
What is it you want?
Do you have another picture from the other side of the fish tank? So in other words, the small part where the laser's pushing in, where you're seeing the laser. So you'll be standing behind the laser.
Oh, like from the end.
Yeah.
Yeah, it's in a video. I can find it.
Awesome. While you're doing that, because this is exactly my point, it causes it to appear to bend. And because you're saying your rod is bent physically, water has meniscus, it has physically following the path, and it's a metal rod, you say, so it is reflecting light itself as well. So it can also give that appearance of curve.
But are you saying that the laser beam
The
wasn't
light
curving?
No, I'm saying the light constantly is changing angle due to the coincidence angle. So it's only appearing to be a curve to you, but it's not an actual curve. It's still straight lines in segments.
Oh, an infinite number of 0 length segments?
Yeah.
Oh, okay. But at the end of the day, it still follows a path that is not straight. Can we agree on that?
Apparent path.
Well, it can follow a path through a curved set of eyelets.
Mm-hmm.
So it's not really a curved path.
And you're guiding it with a metal rod. That's my whole point. You're guiding the water with the metal rods.
No, it's not touching it doesn't touch the eyelets. It's
No,
not guiding it.
You put salt water in before. Did you put the metal rod before you made the salt water? Or the sugar water, whatever you did?
No.
You put it in afterwards?
Yeah.
And then you let it sit?
No, I let it sit, and then I saw that it formed a good gradient, and I figured I could see exactly how much it curved the laser beam, so then I curved the metal to match the laser beam, and then I set it down in there carefully without disturbing.
And that's my whole point. So do you understand viscosity changes with density?
It could, but I'm not sure.
So when you have viscosity on that metal bar, it's changing the density, and therefore the light's just following the viscosity. It's following the meniscus. In other words, you're physically manipulating the light path using the meniscus. But I think this is going off the topic again because this is still making my point that we can rather show it's all optical and not physical. That's my whole point to this argument. We have many variables, and the diagram you provided, were they taking any of these perspective variables into account?
Well, I found the video, but Zoom is totally clobbering my browser, so I can't. It took me a minute to pause it, and now it won't play.
We don't see
Do
that
anything.
screen. I don't know if you meant to share that screen or not.
I'll try. I haven't shared it yet. I was going to try to pause it in the right spot, and just Zoom totally scrambles my browser. It like locks up and then catches up, and okay.
I'll let Zoom know.
Oh, now it went to a different scene, and I can't change the scene.
Scene of what exactly?
I had got my video to the place
gotcha.
where it showed the end view. I think that's what you wanted to see, was like an end view looking down through the islets, right?
Yeah, from behind the
Keith?
very cool.
Yeah, and I found that spot in the video, and then it locked up, and then later when it unlocked, it was in a different place.
We'll give you a second. So if you guys want to join the debate, you can do so by going to Debatism or emailing Debatism at Outlook. You can do it that way, or you can go to t.me/Debatism and put your name in the hat there in the Telegram group. That would be the best way. It's best if you have a partner or you got somebody you want to debate. Maybe you are talking to somebody on Facebook or something and you want to bring it here. Just reach out. We will get you scheduled. Okay, now I get that. Now that's showing.
Can you see what I'm saying?
Okay, can you see that?
Yes.
Mm-hmm. So,
Yes.
so you placed it before you, but that looks straight.
So yep, because the light, even daylight curves in the gradient as well.
But
and so the daylight angle also is curving. What's that?
So you see the angle of incident and the refraction just from our normal atmosphere, and everything changes the way things appear. You understand?
Well, I understand that the density gradient caused a physically curved piece of metal to look straight.
Great. So we can say, so from the side it causes something to look curved, and from the front it causes something to look straight.
Except from the side, the actual physical curve of the metal beam is what we were seeing, because when I took it out of the water and laid it on the floor, it was still curved, right?
How curved was it there?
Just about like here. I think I found the spot.
Great. So my whole point again is, what's optical is not physical.
But in this case, the path of the light was following a physically curved path, right?
Because of the meniscus. Like I explained, it's just simple physics.
Well, isn't the meniscus the thing on the surface, though?
When the water you got in there, the density has changed. So the viscosity has changed. That means there's a meniscus there. It's like when it probably snows there by you. And it snowed, and all of a sudden there's snow on your car, and you got your different layers of snow. The more it packs on there, the thicker it gets. That's what was happening there. So it had to follow that denser path. It had no choice because it was changing coincident angle thanks to the bent path. Have you tried doing this with the straight rod?
Yeah, I put a straight rod in there, and it appeared curved until I mixed up the gradient.
Yeah, so that's my whole point. I think you're missing my point altogether. The point is, which you're validating 100% for me, what we observe is three-dimensional, okay? So it's all optical. And you are trying to claim that what we observe optically and based on three-dimensional space, which we see optically, is physical. That's the issue.
Well, let's see if we can. I think we're kind of getting in the weeds. I don't think you could support. I don't think you could find evidence to support a meniscus between or at a density gradient. But let's see if we can get back on the topic of perspective. I think we might agree that refraction can cause varying amounts of apparent displacement of an object. Is that true?
Yeah, displacement, yeah.
Okay. But are you saying that, let's say for the sake of discussion that on the particular day that I measured that angle to that mountain, there was no displacement due to refraction. It was just somehow a perfectly non-refractive day and refraction was not playing a part. Are you saying that what I measured is still possible on a flat Earth, or are you saying that that was only possible with refraction?
There's always refraction. There's no day where there's non-refraction. Refraction's always a thing because we look through the atmos. And there's temperature gradients, there's pressure gradients, there's fog, there's water vapor in the air. Even dust particles would cause a difference. But I mean, like, that's only the one variable. Refraction's only one variable. We've got parallax, we've got foreshortening, we've got the angle that gets limited, you've got angular size change. You see, there's just too many variables to take into account to say, hey, hang on, what I'm looking has to be physical. Because you even agreed, the further you look at something, the more inaccurate your measuring device would be.
Well, everything has inaccuracies. Even if I have an inaccuracy of 1 millimeter, I still, that doesn't, 1 millimeter would not invalidate my measurement. If there's 6,200 and whatever feet missing, then 1 millimeter does not invalidate my measurement. We need to find some plausible source of error that is enough to account for 6,000 missing feet, right?
There's no missing feet. That's my whole point. That's why I said you got foreshortening, you got parallax, you got refraction, you got diffraction, you got the limiting angles, you got everything. There's no missing feet there at all.
Oh, okay, so geometrically speaking, by the way, am I over talking anybody? My computer's lagging so bad.
No, we're fine so far.
Oh, good. Okay, so geometrically speaking, what should the angle be? If I had, instead of using light, I had taken a super tight, weightless, super strong tightrope and strung it from the top of the mountain down to the top of the other mountain, pulled it so tight it was perfectly straight, and then I put a level on there and measured the angle. What would that be? The half a degree angle that I expected if it was a physical rope?
It would still be half a degree measured, but you would see a different thing, because remember, due to perspective, things converge to level. And just like you had your level now, quote unquote, at the person's base, it doesn't really matter because it's such a small time increment, it will converge to the level. So if your theodolite is set level, which you have to do for your horizontal reference, everything in the distance, the further away it goes, the more chance it has on converging to that level. That's how we say things converge relative to eye level, and that's due to perspective. So everything below your feet have an apparent rise, and everything above have an apparent drop towards that convergent line. So that's why you can't really take and say, oh, it should be this high. Orthographic view doesn't take that into account. Orthographic view doesn't take angular size change really into account. All it does is it keeps it as the same angle. Well, the angles change, but it keeps it as the same actual size going through, while it's ignoring parallax, ignoring foreshortening, ignoring refraction, ignoring diffraction. There's just so many variables that you can't account for. And I think it's actually wrong to say, look, 105 miles away with a theodolite that's not made to actually be accurate at that distance means it's validated for Earth curve after ignoring every single aspect of optical phenomena.
Can I just say something real quick?
Go ahead.
Just for the record, the theodolite is made for very great distance. They've been using them over 100-mile shots for 200 years. So please stop repeating that false information. I know you believed it, but it's not true. I'll give you the manuals to all my theodolites, and none of them say that they're not made for that distance. They list all kinds of limitations, and the maximum distance is not one of them. So it's false information. Please don't spread it.
Got you. Sorry. Go ahead. That was my bad.
So, no stress. You got a Nikon, correct? A Nikon theodolite. Can you hear me?
Oh, now can you hear me?
Yeah, I'm managing the mute button, so that's why I think we're getting confused because you're trying to do it as well. So we're doubling up. Just so you know. Go ahead.
It keeps popping up and says the host wants to unmute you. Is that okay?
Yeah, you can hit OK on that.
Okay, that's all I was doing.
Okay.
Can I share screen?
Go ahead.
Okay. You're just gonna have to end your screen first.
I'll do it for you. There you go.
Sure, thanks. This is, you got the Nikon. I don't know if it's the NE100 to 101, but it doesn't matter. I can bring up both because this is from Nikon site itself. You would agree that with distance, the accuracy changes, and it gives the field of view at 100 meters to 100 feet, 2.3 meters, 1 degree to 20 minutes. You'd agree? Because that's what it says there.
Yeah. But do you know what a field of view is?
Yes, I know what a field of view is.
Okay.
It's what you're able to see in your scope to a maximum 360.
Okay.
Mm-hmm. But like I was saying, can you show me citation where it says you can see over long distances? Because I got another one that says you can't see further than 2 kilometers for accuracy. Let me see if I can get it quickly.
I still don't see what the field of view has to do with anything. That's just the field of view.
You're looking through a telescope. That's the field of view.
Yeah, but how does that limit? How is that any indication that you can't focus on something that is 100 miles?
Field of view is maximum. So if you got a accuracy tolerance of, let's say, 0.01 or whatever, and the further away it goes, it's going to change the accuracy. So as far as you go, if the tolerable inconsistencies can only go up to, let's say, 200 meters or 2 kilometers, and you're taking it 105 miles, you're way past the accuracy of the theodolite. Now, your field of view is based on your optical scope. Because you're using a theodolite, it's optically measured. You actually got the stator hairs in a telescope. So that's why you got a field of view limitation. Just like you can only see so far with anything, your eyes, a camera, anything, a theodolite also has limitations to how far you can see. And like I said, due to perspective, it converges, so therefore it gives a field of view limitation. Accuracy and horizontal distance test. This is by ScienceDirect.com. It is noticed that the best accuracy is obtained at shorter sites. This is true for all levels used in this test. The distance accuracy deteriorates gradually as sighting distance increases.
That's not for a theodolite.
This is from... Yeah, I'll get it on.
That's for an auto
actual
level.
scientific paper they did for this, mate.
Yeah, but it's not about a theodolite. It's about an auto level. That's a different instrument.
Let me check quickly. I'm sure it was theodolites, though.
It said digital level. That's definitely something different than a theodolite.
Optical and digital levels. It's for optical and digital levels.
Right, but that's
Na2 and
not
Na3s. This is research 3 levels. The optical levels, NH2, Na2, and N3 from Leica. And the digital level, SDL30 from Sokeo, were subjected to distance measurements accuracy test. A baseline line of length of 1,000 meters. was first established and divided into 10 equal parts using geodetic means. This was then remeasured with each of the
Hey,
3
Keith?
test levels.
Yeah, this is the wrong instrument. This works on an entirely
Na2
different
and
principle.
N3 is not a theodolite.
The
Is
levels
Na2
are
not a
not theodolites.
optical level?
That's not a theodolite.
Theodolite's not optical.
Well, yes, they're optical, but not all things optical
Okay.
are levels.
No, I didn't
Right.
say that. Just go looking.
Well,
If it is auto level, then I'm going to concede then it's auto level. But my point still stands. It's optical, and optical have fluctuations in pulse direction due to polarization effects occurring to the line fiber and the optical amplifiers. Propagation.
yeah, but look at the amount of the errors, and it does not come even close to accounting for 6,000 feet.
There is no 6,000 feet missing. That's the whole point.
Okay. So is there a way that let's say I know the distance is 105 miles, and I know the elevation difference is 5,245 feet. Is there any way known to mankind to calculate what that angle should be? Because earlier you said that the things above eye level recede down to eye level, right? They converge towards eye level, and you also said that things below eye level converge up towards eye level, right? And they meet at eye level, right? In the distance?
Relative to eye level, yeah.
Okay. So then how come the top of the mountain that was a mile higher than me, instead of converging at eye level, it converged below eye level? And how come the bottom of the mountain, it should have converged up also at eye level, but it didn't. The whole thing moved down, right?
Yeah, 105 miles. Do you know how much different temperature variations you have between 105 miles from you to that target? Jesse? I think we lost him.
That you were just too good. He didn't know how to answer that one. Let's see if he comes back. 1 second. He did have bad internet. Let me fix the screen here. Now, put myself.
I'll be debating myself tonight, guys.
There he's.
There we go.
Let's flip you guys again. There you go. You dropped out. Jesse, go ahead where you left off.
Yeah, my tab crashed again.
I'll tell
All
Zoom. I'm on the phone with him right now.
Okay. So I don't think the temperatures were significantly different. It did match the globe model very closely, like within 18 feet of the globe prediction according to the modern surveying standards. So call it a coincidence or whatever. But I'm asking you, if we could account for the temperature, if we could account for all of that, how would we calculate that angle? Or is that just something that's unknown to mankind and the globe model just somehow magically predicts it?
I find that we are calculating it. The only problem is we are counting that optical phenomena as physical. That's the thing. So it's hijacking everything that's optical and calling it physical. But like I said, temperature variation between 105 miles would be insanely vast, especially if you're on top of mountains and you have in between mountains, you have wind that's happening. You got clouds even change the temperature of the thing. So yes, temperature is going to play a crucial role. And like I said, with the further distance and the angular size changing of the mountain, which causes it to converge and compress into the convergence zone, if you have a little bit even of temperature inconsistencies or changes, it's going to cause it to drop, or maybe even the air in front of it to rise, and therefore give it a distortion underneath your feet.
Okay, could we go back to my question about the tightrope? If we strung up a tightrope in real life, like a real super tight, we strung it up, and we took and put an inclinometer. Do you know what an inclinometer is?
Yes.
Like you set it there and it like measures the angle. Okay. Would we measure the half a degree, the half a degree, based on the geometry of the distance and the height?
Yes, but what you would see would not seem like it's looking up. That's what I'm saying. The physicality, just like remember I showed you in the beginning with Skyfree with the laser? The laser light was hitting at exactly the point where it was supposed to. But according to the observer looking at the laser, it looked like it dipped below the horizon. But the laser light itself still shot and hit exactly the same position. this is how it would be. That hypothetical line that would be a physical measurement. Great, but that's not optical, that's physical. You optically looking at it would still make it look like it's lower because it's so far away thanks to perspective.
So
you can test this. Sorry, you can test this out in your living room if you wanted to. Remember I showed you that paint cans showing that foreshortening in my spray booth in the earlier. It's the same thing. The paint cans are physically that height. The light is physically the same height. It only appears to drop. I can take from each paint can, I can take a rope straight to the observer and it will give exactly that angle measurement. But the eyes would show it to be lower because it's optically observed.
Okay, so what if we've got this tightrope strung up real tight, and it's straight and it's half a degree upward slope, like I have expected marked. If we then took an amazing, a powerful laser and put it on the top of the mountain peak, right, 2 inches from the rope, 50 millimeters from the rope, pointed it parallel to the rope at the observer, and that laser beam made a nice green glowing pencil line 2 inches parallel to that rope all the way down to the observer. Mm-hmm. Would the laser beam run parallel to that rope, or are you saying that the laser beam does not follow this?
It will still follow the rope. It's just going to appear to be dropped optically.
Okay,
so it's not physically dropping. It appears to drop. It's an optical phenomena. That's what we say even with horizon. It's an optical thing. It's not a physical thing. It's only a position based on optics.
Okay, so you're not saying that the laser beam would like curve drastically compared to the rope. It would basically just follow the rope.
This is if we're playing no refraction or anything.
Right, without refraction.
Yeah, then we'll just follow the actual path.
But if I pointed my theodolite at the laser, so I could see the laser right dead in the crosshairs, right dead in the crosshairs, I'm looking up and there's the laser, would the theodolite be pointing up a half a degree or down a tenth of a degree?
I don't understand what you're saying.
Well, let me share my screen. Maybe the visualization will help. Let's see, this is number 120. Allow, and there. Can you see my screen share?
Mm-hmm.
Okay. If we had a laser on the top of the mountain, right up here, can you see my mouse?
Yep.
Yeah.
Oh, cool. Okay, right up here on the top of the mountain, and the laser beam is shooting right straight parallel to the rope, hitting the observer right down here.
Mm-hmm.
When the observer points his theodolite at the laser beam, what angle will the theodolite be measuring? Will it be pointing upward, or will it be pointing downward at the 0.1 degree where the top of the mountain appears?
It will be pointing wherever you are optically using it to follow the point source.
Well, naturally, but I'm asking where that would be, if you know. And if you don't know,
where you remember, theodolite is optical. So you are setting a horizontal reference. Okay. Now you are using that horizontal reference outwards using a scope. So if you have that convergence already there optically, you're going to point your theodolite at that optically already set position. So it's still making my point.
So it would be the theodolite would be pointing a tenth of a degree downward, right? Since that's where the top.
Wherever it is showing that day of convergence.
Okay, so on this day, I measured the angle to the top of the mountain at negative tenth of a degree. So you're saying on this day, in this conditions, the laser would have also measured a negative tenth of a degree, even though it's actually parallel to the rope, which has a positive half of a degree slope.
Yeah, because the thing you have to understand with perspective is it's only having an optical convergence. It doesn't physically bend. Just like when you look out at railway lines, it doesn't physically converge. It just appears to converge. You can measure those railways. It's exactly straight, perfectly straight. Lasers, the 2T. As soon as you look at it, it appears to follow that convergence path. It's because it's only optical. This whole debate is you making my point. It's optical and not physical.
Okay, so what if I took a 100-foot long piece of wire water pipe. What do you call it there? Like a piece of steel pipe? It's long and straight, and it's 1 inch, or it's about 25 millimeters in diameter. Do you use metric or inches?
Metric.
Okay,
It doesn't
so it's
matter.
it's about 25 millimeters in diameter, and it's about 30 meters long. And I take this pipe and I set it up so that I can see the laser beam right through this 30-meter long pipe, right through the center of it. The laser beam is actually going down the center of the pipe. I can look up and I can see the laser beam through that pipe. Now I take my inclinometer and I set it on that pipe. Will that pipe have an upward slope of 1/2 degree like the rope does? Or will it have that 1/10 of a degree downward slope like the theodolite shows?
The inclinometer will follow the angle it's placed upon. So if it's a physical angle, it follows that physical angle. But it's still not, an inclinometer is not optical.
Okay, but what about the pipe that the laser beam is passing through? Because the pipe is physical, right?
And it follows the exact same path you set it at. What you see and what it does is two different things. It's just like if you're standing on a roadside and you see light poles. You understand they're converging downwards. You understand it's not physically dropping.
Right, I understand that, but
it's the same thing. Now you can measure those light poles at exactly the same heights above the ground. Okay, you can measure them physically using an inclinometer, just like you would. It measures a certain degree angle. But what you see and what you measure are two different things.
Right, and that's why I'm trying to get to the bottom of it with this piece of water pipe, right? So that's why I'm asking you, if I set the water pipe up, let's see, here, water pipe. I set the water pipe up so that the laser beam goes right through the center of the water pipe, right? All the way through. Will that pipe be slanted at the positive 0.5 degrees like the tightrope is and the laser beam is, if the laser beam is going through the middle of the pipe?
That's physical, so it will, yeah.
Okay, so if I put the inclinometer on the water pipe, then it will measure the upward slope of 1/2 degree, right?
Because it's physical, yeah. It's not optical.
Okay.
But now you go stand next to it, use your theodolite, and point to it. It will...
Okay, so what'll happen if I take the theodolite and line it up to the water pipe? I already got the water pipe pointing up, right? But now I got the theodolite pointing down, right? So how does the light come down and then somehow suddenly turn up into the theodolite at that last minute? See what I'm saying? Because the pipe's slanting down, so the laser beam is coming down towards the observer, right? But somehow you're claiming that it would suddenly bend over 0.6 degrees up into the theodolite, right?
No. Light points wherever you're looking. If you got a theodolite pointed in a position, that's where the light's going to come into the sensor, into the scope.
Well, what if I have the...
This is actually a straw man anyway, and you're still, again, making my point. Everything physical for measurement will give a physical measurement. Everything optical through your theodolite uses optical measurement, okay? So that's why it is only accurate up to a certain degree. You can't use it for long distances up to 100 miles away because you literally cannot account for the optical variables. This is what I'm saying. You can physically shoot something, measure it perfect, but as soon as you're looking at it optically, a theodolite or your binoculars, your eyes, camera, doesn't matter, it appears to converge and therefore it has a different apparent position. And this is the reason you can't use a theodolite at such long distances, because it's an apparent position you're measuring. It's not a physical distance.
But we've got kind of a problem here. You, my friend, have kind of a problem here. Because we've just agreed that the light is coming down at a 1/2 degree downward slope towards the observer through the pipe. Inside that pipe, that laser beam has a downward slope. Now you're saying that the theodolite will somehow see that as coming from below, even though it's coming from above. So that means the light would have to bend angles right there in front of the theodolite, because otherwise, how far does the theodolite doesn't know how far the light came from? How, if I do this test on a scale model of 100 feet or 105 feet distance and 1 foot rise, just a scale model, then I measure the positive half a degree, right?
Yeah, but you're pivoting your theodolite up and down to get your measurement, correct?
Correct.
Yeah. So once you've already got your established horizontal and the pipe's physically put that way with the level, you're just looking at it with your theodolite. If you're pointing it down, that's not going to change that the physical pipe and that laser light is hitting a point. You are looking through it, measuring it with your theodolite at an angle. Get it? But what you see through that theodolite doesn't determine what's physically happening. It only appears to have a different path because it's optical. You're looking through an optical scope. It's like putting glasses on. Some people can't see without glasses. As soon as they put on, they can see because the light is reflecting at a certain increment angle to get to your eye, so you're able to see. That's why some people can see far distance, some people can see close distance, because light reacts differently. Distances change, mate. Distances optically changes to physical distance. I mean, I don't know if you've ever done long-range shooting before. Have you ever shot a rifle long-range before?
Not long range, no.
Okay, let's just take an example, shooting 200 meters. And you aiming at a target. In your scope, you think, yes, that crosshair is perfect on that target. But as soon as you pull the trigger, whoop, it goes to the right or above it or below it. But that scope was perfectly on that target. Okay? Would you agree then that was just me looking optically and thinking that's where I'm pointing? It's the same with the theodolite. It's optical positioning. It's not physical.
Well, I don't think that's a good analogy, because when you're shooting long range, there's a whole bunch of variables that don't have anything to do with optics, like the bullet and the winds. And the bullet obviously has drop, and it's affected by winds drastically and stuff like that. But the problem we've got right here is we've agreed that the light is coming at a downward half a degree slope towards the observer. And you're saying when I then line my theodolite up to that pipe, the theodolite will be pointing down, but somehow seeing the laser, it won't be pointing down?
Listen, I don't know if I have to draw this. Take my arm, for instance. This is the physical slope angle from that pipe. This is the physical pipe.
Okay.
You take your theodolite, okay? You are now aiming it at the same angle, correct? Because you have to try and get the angle. Or are you just trying to be dishonest and say it has to go down?
No, I'm saying
okay, so you're pointing it at the same angle, but optically you're looking through that scope, which makes it look like it's this way. It's not actually this way. It's physically this way. It appears to be this way thanks to perspective. It's called convergence.
Oh, so you're saying that the telescope, the actual physical telescope, will be pointing up at the half a degree.
Wherever you're pointing it.
But it's not, because the theodolite actually measures angles. Let me, can you see my screen share here? Let me go. This is just a logical diagram of how a theodolite works, wherever it went to. It actually has a very accurate leveling device built in, and then it actually physically measures the angle of the telescope. So I'm not just looking in there and saying, oh, I think that's about a half a degree. I actually line the crosshairs right dead on to that laser or that mountaintop or whatever, and to physically line that telescope up with the angle of the incident light, and then there's an actual physical encoder that counts the actual arc seconds of rotation relative to level. So the telescope is physically and objectively pointed upward or downward or whatever. And in the case of this mountain, it's physically pointed downward. If I were to set a level on there, it would show that it was pointing down at a tenth of a degree, right?
Okay, great. So this is my whole point. You're making it perfect. So you take the same tree and you move away now. So your distance is increasing. You would agree that 31 degree elevation angle is going to drop physically on your theodolite.
Absolutely.
Thank you. So the angular size change due to distance causes your theodolite to physically drop. But is that tree physically dropping, or is it just getting smaller due to angular size change?
It's just getting a smaller angular size, obviously, but this is my question. How far back do I have to go before that 31 degrees becomes a negative angle? That's my question.
Depending on the day, probably. Like I said, still making my point, it's all optical. So the further you go away, especially your mountain 105 miles away, there's a lot of refraction in between. Temperature invariations, you got parallax, you got foreshortening, you got diffraction, you got refraction. Like I said, everything is optical. So that's why it appears to be lower. Back to your, even your tree you just saw, you agree. The further you go up, your theodolite is physically tilting now to keep up with that angle. The tree is staying exactly where it was. It never dropped, never got smaller, but you are physically having to adjust your theodolite to see the optical observation measurement. Well done.
Right, but the problem, what you haven't addressed yet here, Keith, is that the telescope on the theodolite in reality was physically pointed downward 1/10 of a degree below level. But we agree that the light was coming to the observer with from 1/2 a degree above eye level. So how, and you're telling me no, that the telescope was actually pointed up, but I just thought it was pointed down, but that's not possible. No?
No.
So
you physically pointed it down to measure optically. Okay? You had to physically measure it downwards. That's how the theodolite moves on the pivot, up and down. You physically have to move it down to keep with that point of measurement. You are taking a physical arc to a optical observation.
So what caused that 2/3 of a degree of change of angle between the light coming through the pipe and then turning and going up into the theodolite? Because if the theodolite is pointing down, the pipe is pointing up, and the light somehow gets through the pipe and then turns and then goes up into the theodolite. How does that work?
You're not getting it, do you? It's very simple. It's optically looking like it's lower. So if you have a physical pipe sitting like this and you got a theodolite physically looking at that angle, you won't be looking at it like this physically because you're following where the pipe looks. But when you're looking through the scope, it will appear to look this way. But it's physically this way as you measured, but it appears to look lower because of perspective, just like we explained with the tree.
So are you saying that the theodolite's telescope will be pointed upward or downward?
It points perfectly where you are optically seeing the observation.
And that's what I'm saying is what will the actual angle be?
If something's right against your theodolite, you're going to point it straight at that angle, which is perfectly right at your theodolite. So it's not really, it's actually sort of a red herring. I can place it, but I'm just trying to explain to you, even in your own paradigm, that it's physically at an angle, but optically at a different angle, especially with longer distances. The longer the distance, the more perspective.
But that doesn't explain. We agreed that the laser light going through the 30-meter pipe is coming at a downward slope of 1/2 a degree towards the observer, right?
Yeah, I'm just going to quickly see if I can maybe draw it for you.
It's drawing time with Flatzoid. Here we go.
And we can use paint because we know how the ballers love paint. I can share my screen quickly.
Yep.
But I'm enjoying this though, by the way.
Me too. And I appreciate it. Thank you.
Okay, you're ready.
Share. Okay. Let's say we got our one mountain and we got the higher mountain, as you say. Okay. And you sitting on here, you're going to make a reference. That's your datum. You got your vertical, you got your horizontal, and now you got your physical pipe now. I'm just going to set the orange pipe coming down to the observer. That's physical. You agree?
Yeah.
Okay. So the observer is looking at, let's say, 40 degrees, whatever. Just saying it's looking 40 degrees upwards physically. Now, notice this is orthographic. Okay, that's what you measured. Now, what you're looking through when you look through your scope, excuse the, just going to give a rough kind of steady thing, okay? Doesn't, and you're going to have the mountain. It's going to appear like this. You understand? It's not physically below.
No, bring
it
the
only
mountain.
appears that way.
Yeah, bring the mountain up a little bit. Put the point of the mountain
It
right.
doesn't really matter. We can make it like that. It really doesn't matter. The point is, I'm trying to say, what you're observing here is not what you're looking through your scope.
No, you're not drawing it right. When you use a theodolite, you line the crosshairs up exactly on the mountain peak, right dead on.
That's my point. And where you're looking at the mountain peak, this mountain peak is appearing here. It's not physically here. It appears there, and then you going and you're making your measured line towards the apparent mountain peak. It's physically up there. It only appears to be below. You get it?
Right, but my question is, what causes the light to change the actual angle? It starts out at
refraction.
So is that the only thing that's causing that 0.6 degrees of change of angle?
Angular size change, perspective, parallax, foreshortening.
Straws.
No, I gave you actual demonstrations in my presentation, even some by you, that make my point.
But none of them address the question of what's causing the light to redirect by 2/3 of a degree after it comes out of the pipe and then goes into the theodolite.
Again, you're following that physical path. You're looking through an instrument that sees it optically. So you literally pointing that optical laser or your theodolite scope at what looks to be the position. It's a refracted position, if I was to put it that way. Just like you guys look at the sun, you would agree, according to your model, the sun's not even where it is. It's at a refracted position.
Yeah, degree or
so
something.
If I point the theodolite at the sun, and it gives me an angle measurement, does that mean that's the actual position of the sun or the refracted position of the sun?
It would be the apparent position.
So optical with physical measurements.
Right. But that's a lift, not a sinking. And we're trying to understand this 6,000 feet of sinking. But let me ask you this. Evidently, you don't understand how theodolites work. They work just like rifle scopes. You have to point them where you want to point them. You line the crosshairs right up to the center of whatever the target is, and that's the optical center all the way through the optics. So they measure the angle of the incident light.
Okay, Flatzoid, are you?
Sure. I just had before the time's up. Okay. First of all, I know how a theodolite works. I've been explaining it to you all night, right? Yes, you set a horizontal datum, then you point it at the optical measurement to get your angles. Okay, this has been explained. I've been explaining to you all night. You've been validating my arguments. So instead of trying to tell me what I do and do not know, just concede. It's an optical measurement and not physical. I give up.
So evidently you don't trust theodolites, so let's throw that off the side of the mountain, and let's use the pipe instead. Okay, so if I were to use a pipe and put a very accurate inclinometer on it, are you saying that I would then measure the mountain to be a half a degree above eye level using the pipe with an inclinometer?
If you could get that right somehow, which would be impossible, but okay, yeah. It's a
I can get it right.
Measurement.
I can get it right.
105-mile pipe.
No, not the pipe only has to be like 100 feet, 330 meters.
Nope.
Remember, if the laser beam is going through the center of the pipe has to be lined up. If it's not pointing at the right place, the laser beam can't go through the pipe, right?
Remember, the contention is 105-mile peak, 105 miles away peak.
Okay.
So if you are taking it physically from that peak to the observer, that means you need 105-mile long pipe with the laser shoot right through it from 105 miles away. And
Well,
then you
let's
have to take your theodolite and point it. Yes, point your theodolite to where you see the peak. And you'd see it will line up perfectly with the hypothetical pipe because it's not actually dropping. It only appears to drop while physically measured.
Okay, so maybe you misunderstood my thought experiment earlier. You understood we've got a tightrope from the mountain peak to the mountain peak, right?
Mm-hmm.
Okay, then we've got a green laser beam 2 inches from that, 50 millimeters from that, going parallel to the rope, right?
Mm-hmm.
Okay, now we take a 30-meter long, 25 millimeter diameter pipe. It's not 105 miles long, it's just 30 meters long, about 100 feet long.
Mm-hmm. And lay it over it.
And then we line it up at the observer's end. We line it up so that the laser beam goes straight through that 30-foot or that 30-meter piece of pipe.
Mm-hmm.
Okay. Will that 30-foot or that 30-meter piece of pipe, will that be sloped up at the same rate as the rope, or will that be sloped down where I see the mountaintop?
Physically sloped up because it's physical. But as soon as you take your theodolite and point it to the peak where that comes from the source, it will appear to have dropped.
Okay, well, don't worry about the theodolite. We threw that off the mountain. Don't worry about that one.
Okay, with your eyes. So according to your eyes, it will look like it's dropped.
Oh, okay. So now let's say we radio the guy on the top, have him shut off the laser beam, and we look through the pipe. Okay? Now the pipe is still pointing up a half a degree, right?
Mm-hmm.
We look through the pipe. Are we going to see the mountain peak through the pipe?
Yeah, because you're looking through a small field of view.
But you won't, because the mountain peak appears a tenth of a degree below eye level. So if the pipe is pointed up a half a degree, you won't see the mountain peak through there. Sorry,
the thing is, it's physically stuck to mountain peak. Physical, okay? It's not wobbling or changing. It's literally rigid. So if you're looking through the pipe that's only got a field of view looking straight to that point source, that's what you're going to see. So your angle is literally going to coincide with what you're seeing, and it's literally measuring because your field of view is to a pinpoint. It's not going to appear, no, you don't see it anymore. That's just insanely dumb to say.
Except it's true.
You want to try it out?
Actually, I did it at 21 miles with about a 1 meter pipe, and a building, and it's true the whole building had dropped down below where it should have been in the view of this tiny little pipe.
Great. So it's optical, not physical.
Well, how can it?
Remember, you didn't have a rope. You didn't have a rope lined straight from that building 20 miles away, did you?
No, but I had the pipe. I had a 1 meter pipe.
That's my whole point. Okay, the pipe in the field of view is going physically to that position.
Okay.
Your eyes looking further out, the further you go, the more something converges to level. Simple perspective, mate. I don't know how much more I can explain this to you.
Okay. Well, let's say for the sake of discussion that I did take a pipe up to the mountain peak, and I did accurately measure the physical angle of the pipe, and I used the pipe as a sighting device, and it also showed the top of the mountain with 6,000 feet of missing height. In other words, the pipe was pointing downward toward a mountain peak that was much higher. How would that be possible on a flat Earth?
So you're saying you physically took the pipe, but now you're looking physically down at the pipe.
The pipe is physically slanted downward.
Okay. That would be a physical measurement, but that's a hypothetical that's never been done.
Well, I've done a scale model one enough to know that it's going to work.
So you can do 105 miles of having a rigid line.
No, the pipe's not going to be 105 miles. The line of sight will be, 100 miles or something. The pipe will be long enough to unambiguously establish the physical path of the light from the target to the observer, right? The light will be going through the pipe to the observer from the target.
Field of view. So you have a field of view, optical. Do you know with distance how difficult it is to point something, even a laser, to pinpoint something at far distances? You know, it's very difficult to get a very accurate pinpoint position.
Yeah.
So how can you guarantee your pipe that you are now placing as in your angle you want it to is perfectly hitting the site that you're supposed to have it at?
I'll just sight through it. I'll look through it.
That's the whole point. You can't, because you're using optics to sight through it. So in other words, you're pointing it to a already optically altered apparent position.
So are you saying that the pipe no longer points at the mountaintop in order for the light from the mountain?
It points to wherever you're pointing it.
Okay, but let's say I line the pipe up to the mountaintop, and I can see the mountaintop right through that pipe. It's like, you know how we used to hold up like paper towel tube, cardboard tubes when we were kids or whatever. We do that with the pipe, but it's longer, so it's more accurate. We point that, and we can see the mountaintop right in the center of our pipe. We can see the mountaintop, right? Is that pipe going to be slanted upward at the 1/2 degree, like the tightrope was?
Again, using optics to sight with the pipe.
Yeah, we're looking through the pipe.
The object has already, due to optics, you taking optics and you're looking through the pipe. Where is this mountain? Oh, it appears low. So therefore, I'm pointing it there. It's already optically dropped due to perspective. Do you get this?
Well, so I'm just asking your opinion. Would the pipe be
1 minute left
slanted down? Oh, am I out?
No, I was just telling me he has 1 minute left.
Oh, okay. So I'm asking, would the pipe be slanted down, looking down at the mountain, even though the mountain was higher?
It would be wherever you're pointing it to.
Okay. Because we agreed earlier that if there was a rope and a laser beam, then the pipe would be slanted up at a 1/2 degree, right?
Physically.
Physically, yeah. So theoretically, we should also see the top of the mountain through that pipe, right? If the laser's on the top of the mountain, the laser light is going right through the center of the pipe, straight through, then all the other light that's coming off the top of the mountain should also be going through that pipe, right? So we should see the top of the mountain if we look through that pipe, right?
40 seconds, Jesse.
Yeah, because the rope is physically set at the mountain to physical observer height. So it's a physical angle spanned across. Physical.
But the pipe would still have the same angle even if the rope happened to not be there, right?
No.
Oh, the pipe's angle that allowed the laser beam would change if the rope was removed?
Remember, you need the rope to place the angle for the pipe correct. If you don't have the rope, you can't place the pipe correct because you'd just be using your eyes, which means optical, which would mean it seems lower, which it's not actually lower.
No, there's a laser beam. Remember, there's a laser beam that we're getting the green laser beam, right?
And lasers also refract, mate.
Well, but we agreed for the sake of the discussion that the laser was going straight like the rope and through the pipe.
Again, it would point physically where it is pointed from. If you have physical set boundary, your optical measurement would literally just be optically going against what's physically measured. I don't know how much more I can make this, because that's all that it is. It's optically measured.
Even though the pipe is physical and the light's going through the center of the pipe. I think that should establish the physical path of the light. If the pipe is physical and the pipe is physically sloped at just tell me when I'm out, Jaron. I can't see the clock.
You're out. You should be able to see the clock if you go to...
Oh, there it is.
Okay. Go ahead, Flatzoid. You have 18 seconds to finish this off.
Okay, cool. So I'm just going to end this off. The whole night he's been validating my point. You have to physically go and take a measurement that's based on optics. So they take optical measurements and claim it to be physical without understanding it's all optical. I rest my case.
Okay, each get a minute conclusion. Starting with you, Jesse. Go ahead and start. Wait, was it you first? Yeah, you were first, right?
I think so, yeah.
Okay, go ahead. 1 minute, and whenever you start, we'll start the clock.
All right. Well, thank you, Keith. Thank you, Jaron. I really enjoyed that. I am not satisfied with my understanding of your answers. I hope we get a chance to discuss discuss it some more. And I would also like to discuss with you sometime how your claims can be tested in the real world.
Anything else?
I think that'll do it. That's all I can think of.
And a minute for Flatzoid. And if you guys have any questions for these guys, you can send in a super chat, either YouTube or Rockfin, and they will hang around for a few minutes and answer questions. So get those in if you have questions for them. Go ahead.
Awesome. Thank you very much. I did enjoy this. Thank you very much, Jesse. I'd love to have a conversation with you. Like I say, you're very respectful, and I enjoy that a lot. And I think we can have a great get together and have a good front and back. I am very frustrated, though, because I tried very hard to explain everything is optical. Even every explanation you try to bring relies on your observation being optical, which means it's in an apparent position. And the fact that I brought actual demonstrations to the party to make my claim that I can demonstrate my things on small scale proves that I am the one with the evidence and not you. You guys are claiming physicality where it's based on optics. And thanks everybody for coming. Thanks, Jaron.
Awesome. Thank you. It was very easy.
Let's do refraction next time.
All right. Let me check out super chats real quick. We've got a couple of them. All right. So up first, we've got I've been banned from Flatzoids channel. This is from IUCH. You know who that is?
Oh, Luch.
Oh, Luch.
Yeah,
okay.
he's a seasoned troll.
I think so. If you could ask him about that, I really appreciate it. Maybe at the end or something. All right. We asked him. It took away part of my happiness since I am a very social guy and I really love our chats. Tell that to Flatzoid too. All right, Flatzoid. You have a...
Yes, sorry, Luch, I had to because the people were moaning that you kept trolling in the chats nonstop and it started pissing people off and I couldn't, get my audience through that anymore. Sorry.
Matthew D. Gregorio, thank you for the 5 memberships. We've got Digital Intel says, thank you, Jaron. Great debate today. Optical and physical are different. Learned something new today. Awesome. Let me check and see if we've got any over at Rockfin. If not, you can ask them in the regular chat now. I'll pick out a couple if there's any in there. And none at Rockfin, so I'll just wait for the chat, see if there's any good questions for you. Yeah, this is an interesting one today. This is an interesting one. I think that we'll need to look at it, think about it, because I think that there's something that is being missed there. Let's see if there's any here. Oops, I'm in the wrong one. All right, I don't think there's any more. Let me see top chat. Anybody have any questions for them while we're here? Why does Big Brother try so hard to cover up Flat Earth, Jesse? You should look into that. Jesse, do you have an answer for why?
I think it's the other way around. You should have seen the weather not cooperating today. I think people do control the weather, but it's the Flat Earthers controlling the weather, making it hard for Globers to do measurements.
Yeah, that sounds about right. Let's see if anybody here. And nope, nobody. How much to crowdfund Jesse's pipe? For 100 miles? It's going to be pretty expensive. Pretty expensive. Bad optics can be physically painful. Jesse, why do you use your theodolite incorrectly? From Apocryphon. Yeah, Jaron, ask Jesse why.
Hey, brother.
Oh, you know who that is?
Oh, yeah.
He claims you use it incorrectly?
Oh, yeah. He likes to say that you're not allowed to use them beyond a certain distance. He's got no source for the claim, and surveyors have been doing it for 200 years. So,
been measuring 100 miles?
Yeah. In 1868, they accurately measured the elevation of Mount. What's the highest mountain in the world?
Well, it depends. If you take it from the center of Earth on a globe, then it's in Fuji, or in West Hawaii, or it's Mount Everest. Depends on the base.
Everest. Yeah, Everest. In 1868, using 1868 era quality theodolites, they accurately measured the elevation of Mount Everest from 120 miles away.
Jesse, somebody asking, can you explain how the atmosphere moves with the Earth?
Pretty good. It moves pretty good, not like lockstep, but pretty close to it.
Okay.
just like air moves with in a convertible with the top off and the windows up. Except better, because there's nothing else that's not moving that would drag it down.
Okay. And see if anybody else. I can't read that. Let's see here. It might be it. The globe model is archaic. That's not a question. Any questions? Last chance before we let these guys go. Do appreciate them being here. And we should have a good, I think we have a schedule next week. I forgot who it is, though. I was going to tell you, but I'm not going to tell you since I forgot.
Well, I know Ozian wants to debate me on biblical cosmology as well, so we should set that up there as well.
Oh, nice. That'd be great. Yeah, Ozian, not a believer.
Yep.
We're all here on accident. You know how the Big Bang works. All right. I don't see anyone else. All right. Thanks, guys, for being here. It was fun. And am I missing? Oh, now there's a few more. Just trying to read these. No, nobody. All right. Well, I thought there'd be a lot more questions on this one, but it doesn't look like it. That's good. I think you guys could do it again, or at least maybe have something where maybe you can explain it a little bit better to him, or make it so that he understands that. I don't know. It was fun, though. All right. Any final words from you guys? Tell everybody where they can find you. There is everybody's links in the description, so you can find Jesse's channel. What is it called again? Jesse what? Only Jesse? Jesse's
From Jesse.
From Jesse.
Like
It's like only Jesse, something like that. From Jesse, that's right. And then Flatzoid's Perspective is linked as well. And he does a show most days. So we'll start with you. Go ahead and say your goodbyes, Jesse.
All right. Well, thank you all so much. I really enjoyed it. And maybe next time, instead of perspective, we can do the whole thing on refraction, because that's a fun one too.
Sounds good. And then go ahead, Flatzoid.
Awesome. Thank you very much for the opportunity. I really enjoyed it. Thank you guys all for coming. You can find me on Flatzoid's Perspective. We're going to have an after show now. So hopefully to see you all there so you can all discuss what we had discussed about tonight, and hope to see you guys soon.
Awesome. Thanks so
Does that
much.
include me?
Yeah, you too.
All right, I'm going to play that song again. This is from Conspiracy Music Guru and Steve, and it's a great song. You'll wake up someday. All right, guys, we'll see you next time. There is no Jeranism show today, but there will be one tomorrow, so look forward to that. We'll see you then. I remind you, do your own research when you do. You'll never again believe all the bullshit you've been taught.
Ready?